problem. It solves the problem and it gives you some solution. But what you want is not the solution MATLAB creates. It's the numerical method that you need to implement. And there are two different types of differential equations. Assume that y of time 0 and then y prime of time 0 is given, like this. Then this kind of problem is called the initial value problem. So this is the initial value problem. And the other type of value problem is boundary value problem. Just a moment. Assume that the conditions are given in this form. Then this kind of thing is called the boundary value problem. What do you think is easier? Initial value or boundary value? Pick one. The initial value problem is way easier than the boundary value problem. In addition, boundary value problem sometimes do not have solution. Depending on conditions, we may have some solution. So theoretically it's tougher, and practically it's very difficult. So we will cover only a few cases later. So mostly the initial value problem will be covered. So to simplify the expression, I will use this kind of thing. I will call x of n, and x of n is the x position when you break this up evenly. So x0 is here, x1 is here, x2. So we break this up evenly. So we usually use the distance h, distance between each node by h. And another expression that I want to use is this one. I will use yn. What is the meaning of yn? Yn is y of xn. Y is a function, then function is evaluated at specific node is called yn. So just notation and explanation. And finally, fn. What is the meaning of fn? Usually, differential equation will be given in this pattern. Some function of xy, right? So differential, first order differential equation will be given in this form. Then f of xy exists, right? So f function is the right side, right? This is the right side of the differential equation. The right hand side of differential equation is called f. Then fn is f of xn, and then yn. Any questions? So these will be used from now on. Then the theory is this. Oh, when we have a function, then we can use Taylor series of this function and then write it in this form. And then Taylor series, right? But let's make it simple. I explained many things already, but let's make it simple. What is the real task? What is the real task? Real task is only one thing. So I will go to the next column and then explain. When you solve a differential equation, we, especially initial value problem, we already have xn position, so xn determination is nothing. Xn determination is already done, right? x0, x1, we know the location. We in fact determine or decide this location on our own. So the key is yn determination. y0 is given by the initial condition. Initial height is given by the condition. So in short, numerical method of solving differential equation is determining the next height. This is it. This is the numerical method. Determining the next height. Next means you determine this x1 position, right? x1 position could be very close to x0 or very far from x0. In any case, you determine x1 position, then real task is determining the height at x1 position that you chose. This is the task. You follow me? So in short, numerical method is just determining the next height. That's it. So how can you determine this thing? And then in our notation, the height at x1 is called what? y1, right? In other words, how can you find y1 is the task. Once you determine y1, then from y1 we solve the same problem. Only change is the subscript change, right? Then using y1 you can determine y2. Using y2 you can determine y3, and so on. So only change is the subscript change once you determine the scheme. Then Euler used this idea. But what I want to say is this one, never use Euler to solve a problem. Because this result is terrible. Never use this, but I will let you know why this is considered. Euler considered this thing, y1 minus y0 divided by h goes to the derivative of y, right? This is Euler's approach. You follow me? The derivative definition. y1 minus y0 over h is y derivative at the point close to x0, right? Roughly x0, right? So from this, can you solve this for y1? What is y1? y1 equals what? y1 equals what? y0 plus h times y prime of x0. And because of the right side of the differential equation, can you rewrite y prime of x0? Because of the right side of the differential equation given. How can you write it? f0, right? So y1 equals y0 plus h times f0 is Euler's method, Euler's idea. Then take a look. Are 0 and 1 absolutely required, or we can change these to any other numbers? It's possible to use any other numbers, right? You can replace this by n, and then it should be replaced by what? n plus 1. Or k plus 1. So we can develop all the necessary ideas. Then let's implement these things. So I will implement this function. For instance, assume that we are solving a differential equation. Assume that we are solving a differential equation. Y prime equals x plus y. Then what is f? What is f? F is what? This is f. Right? Once the differential equation is given, f is given. And then y of 0 equals what? What number do you want? Y of 0 equals what? 2, right? I pick any number. So this is the differential equation. This is y. Then what I want to do is this one, implementing this thing using Euler's method. I will pause and then implement this. So f function is the right side of the differential equation. That is x plus y. Let's do it. So f equals So roughly, this is Euler's method. So we need bookkeeping, right? If we run it, it will show us an error because x0, y0 are not defined. So we need bookkeeping, but I essentially wrote down the essential part of the program. Do you follow me? This is the essential part of the program. Then bookkeeping is saying x0. What is x0? x0 equals what? 0. And what is y0? 2. Do you follow me? So I did bookkeeping. And then I should do this thing to determine the next height. After determining the next height, I want to use this previous height to determine the next height, so I can loop, right? So after doing this, after determining this, I will display h should be determined. H is the size of each subinterval, right? 0.1 is size, right? H. So I will display x1 and then y1. Do you follow me? Do you follow me? I'm solving for the next height. Then next height and then next node here is displayed. And then I return back and do the same thing. Then it will find the same point over and over again. So after displaying it, I should replace x0 by what? x1 and then y0 by y1 to have better value for x0 and y0, right? In other words, we completely shift from x0 to x1. Do you follow me or not? In other words, we don't really use x0, x1, x2 in our program. We just use x0 and x1, x input and x output, y0, y input and y output. And then each time we shift instead of recording these things in array. So let's run it. So take a look. As you can see, initially x1 is 0.1 and y height is 4. And next time 2 and 8, 0.3 and then 16, 0.4 and 33, 0.5 and 66, and so on, right? So we get these kind of results, right? Do you follow me? So each time we determine new heights and then shift and determine new height and then shift and determine new height and shift. So essentially, this frame does not change. The thing that changes is the engine part. This is the engine part. Euler method part is replaced by other method. But except this engine part, we don't change. Do you follow me? Only change happens in engine. Others are essentially the same. Yes? Oh, H is missing. Thank you. So I said H times something, and when I implement, I missed. That might be the reason why it blew up. As you can see, I will see. So this is the result that you can obtain, right? So point 1 has height 2.2, and this. Do you know this kind of error happens not just in the classroom. Sometimes when they program for rocket, they do this thing like this, and they lose rocket. In any case, this is the height result. Any questions? Essentially, programming part is nothing. Take a look. We initialize the function of the right side, right? Function, and then initial variables, and then the distance between each node, and then engine. And then after this, just bookkeeping, right? And then shifting the role of x1 and x0, right? Shifting the role, and then returning back and do the same thing. So essentially, the improvement comes from this portion of the engine. And I used Euler engine to calculate this. Do you follow me? I will not show this kind of programming anymore, because once we develop theory, then we may get better results. Programming part does not change. Theory part changes. Do you follow me? So let's do it. So we want to improve the theory. So to improve the theory, Hoyne developed this thing. Oh, instead of saying y, I will use 1 and 0 so that we don't worry about location. Y1 is determined not by the, so I will show you the Euler side by side, right? Not necessarily side by side, but a little off side by side. Euler here, and then Hoyne here. So take a look. In Y1 determination, up to this point is similar, but H, and then instead of F0, we will have F0 plus F of x0 plus h, and then we need space, right? So I will x0 plus y0 plus h f0. So this is Hoyne's idea. In other words, he removed the dependency. He removed or balanced the dependency, because Euler method depends on the previous point too much, right? Euler depends on previous point too much. So he tried to balance it by using average. Average of f0 value, and then the value that we can get in the next point. So this is what Hoyne did. So please take a look and ask questions. Then what do you get? In the program part, you need to change this portion, right? Change this portion appropriately. It's not very difficult to change this portion. So do you feel the direction? Because Euler just used the derivative definition and then derived the formula. But Hoyne improved it by averaging the dependency. It doesn't just depend on 0 position or 1 position. Roughly it's 1 position, right? 0 or 1 position, average. Question? This is what Hoyne did. After Hoyne did this thing, Wangakara improved this to fourth order method, RK4. So they improved this up to fourth order, meaning when you do Taylor series expansion, you use first order term, second order derivative, third order derivative, fourth order, then this level is fourth order derivative accuracy. So they improved it, and this is what they did. They used K1 value equal to h times f of x0 value, y0 value, and then K2 value equal to h multiplied by f of x0 value plus h over 2, and then y0 value plus K1 over 2. K1 is already calculated here. And then K3 value equals h value multiplied by f of 0, h over 2 value, y0 value plus K2 over 2 value, and then K4 value, h value, and roughly this is what they did. And then after finding after finding 4 different slopes, they average these things. Not just straightforward average, but weight average. How? 1/6, and then this K1, and then 2 times K2, 2 times K3, and then K4. So in short, if we just use slopes, we determine the first slope at x0. First slope determined x0, and then half position advance. We advance half position, and then determine the second slope, and then second slope in different view, and then we advance to the full, and then we determine the third slope. Then we have 4 different slopes, right? We have 4 different slopes. Then we add these slopes and then average it. So first slope, second slope copied, third slope copied, and then fourth. So we use these 4 different slopes using weight average. Then this determines average slope, right? This average slope determines the next position. This is RK4. Do you follow me? So we are finding slopes in many different ways. Euler method just use the slope at the beginning point. Coin method averaged at the beginning and then at the end. RK4 creates 4 different slopes. Beginning, middle, there are 2 middle, and then end. There are 4 different slopes, and then weight average determines the slope. And it is better than all other things. And in some sense, initial value problem has a very nice method called RK4, and then this is, in some sense, the best method. But sometimes the differential equation is very bad. Somehow RK4 may not work, but in many cases RK4 determines the best result. So formula you can find anywhere, but idea is more important. Do you follow me? So we determine the slope at the beginning point, middle point, and then end point, right? The middle point we determine 2 different slopes. And then at the end point we determine, and then we average these slopes to determine general slope from position A to position B. So I will use graphic expression.
If these slopes are all considered positive, what about up and down?
Oh, up and down could be also considered. So take a look. So this is the initial position given by the problem, and we want to find the height here, right? We want to find the height here. Then first thing is using the slope at this point, right? Using the slope at this point. So this is the first slope. So a little bit up, right? And then at the middle point, we determine the slope using some condition. And then second slope somehow calculate. And then at this point, we calculate the fourth slope, right? There are 4 slopes calculated. Then after calculating these 4 slopes, we average these things, right? Twice here, and then twice here, and then 1 time. Average, right? This average will determine the slope. Yes? That is right. To have accuracy, we need small h. If h is too big, then there could be error, right? So h should be small enough. If we use big h, then it can oscillate inside, anything can happen, right? So that's the reason why we don't make big interval. In other words, to solve a problem, it's a good question. I will describe the problem itself too. In differential equation, solution is nothing but the set of heights. So in differential equation, solution consists of this kind of set. This kind of set is a solution, right? This is a solution. So height given in graphics or given in data, right? Numbers are solution, right? These forms a solution. These form a solution. So solution is nothing but point height information like 2, 2.1, 2.2, 2.5, and so, right? So this is a solution. But when you create the solution, it's good to have refined node, right? We have solution height information at many points instead of height information at 0, height information at 10, height information at 15. Instead of this kind of thing, we want height information at many points. Do you follow me? So using small h is essential. Any other questions? So RK4 is learned, then it's time to implement a little bit. So let's implement this in RK4. So I will add, before determining Y1, I will add weight average, right? So weight average is this, 6 multiplied by K1 multiplied by 2, K2 plus K2 plus K3 plus K3 plus K4, right? So this is RK4. So we want to determine K1 through, so K1 equals H multiplied F of X0, Y0. And then K2 equals H multiplied by F of X0 plus H over 2, and then Y0 plus K1 over 2. And then K3 is equal to H multiply F of X0 plus H over 2, and then Y0 plus K2 over 2. And then finally, K4 equals H multiplied F of X0 plus H, and then Y0 plus K3. So I just copied the formula, right? Then it will determine Y. You follow me? So essentially, all you need to do is changing the engine, right? So engine is replaced by Euler formula or Hoyne formula or RK4, right? RK4 changes. So let's run it. So let's run it. Then you get this result. You get this result. So this is the result from RK4. Of course, Hoyne is not very difficult to implement, as you saw, right? Hoyne is very straightforward. So do you follow me? Of course, we can refine this thing. We can refine this thing using smaller h. So instead of 0.01, we can refine it this way, right? And then we can refine this thing using this thing. And we get this kind of result, right? We get this kind of result. Any questions? So differential equation solving in numerical method is finding set of heights, right? Finding set of heights. Then the next thing is system. Assume that you have this kind of differential equation. Y prime equals x plus y. X prime equals x minus y, where x and y are functions of t. So this is the question. Find the function x of t and y of t satisfying this kind of differential equation. So it's a system. So we want to solve a system of differential equation. Then we can develop similar idea. Euler method says this, x0, for instance, x of, now role changes. X is replaced by t. So t is introduced instead of xy now, txy. So t is the independent variable instead of x. So x0 is, for instance, 5. Y0, for instance, it could be 6, right? Any initial condition can be given. Then x0 is 5, y0 is 6, and then we can do the Euler method. For instance, x0 equals, x1 equals x0 plus h times f of x0, y0. Can you do it? It's not very difficult to do it, right? Of course, what is f? F is top function, right? So this is f, this is g, right? This is f and g. F. And then y1 equals y0 plus h times g of x0, y0. So this is Euler idea to solve the system. We can have as many variables as we want. Instead of just x0, y0, we may have x of t, y of t, z of t, k of t, w of t, right? And as many functions as we want. Then, can you do the Hoynes method to this thing? Instead of just multiplying f to h, you can use average of f and the next value, right? And then g and the next value. Then Hoynes. Can you apply the RK4? It should be possible, right? RK4 is possible. So I will, instead of writing down these things, I will show you the summary so that you can directly follow the formula from the description. So as you can see, I will magnify this thing. So this is the idea. We want to solve this differential equation. X prime of t is this one, y prime of t is this one, and I didn't use the independent variable in my equation, but sometimes differential equation itself have independent variable. Mine did not, right, because it is just x and y combination in my example, but generally independent variable t may appear in the differential equation. So let's assume that time 0 gives us 0 position, time 0 gives us 0 position of x and y. Then what should you do? You determine k1 using this thing, similar thing, and then you should not determine k2 directly. Why? After determining k1, you should determine L1, right, which is the counterpart of this k1. Do you follow me? So k1 is determined, then you should determine L1. And then using both k1 and L1, you determine k2, using both k1 and L1. So you do not determine this column by column. Do you follow me? You should determine row by row. Even in n-dimensional case, it's the same. You should not just determine k1 through kn and then determine L1 through Ln and then say, oh, there is a bug. I cannot find the bug. It's a bug. Why? Because you calculate k1 through k4 and then L1 through L4. Why? Because we need values of L1, L2, L3 in the calculation of k. But if you just calculate column by column, then you miss these values, but these values are inserted, then your result is unreliable. Do you follow me? So when you program multidimensional case, you should calculate row by row. So finish the first row calculation, and then second row calculation, and so on. So I saw this kind of mistake many, many times. When you submit and then give me the result, you should be very careful. So in general case, when you have, for instance, k variable, k functions, right? K functions, then you should calculate k1 for every possible variable. And then after completing this k1 for every possible variable, you calculate k2 for every possible variable, k3 for every possible, and k4, and then later do the weight average. So we can handle two-dimensional or n-dimensional, k-dimensional differential equation. Essentially, I explained the key part of ODE solving, And if you have doubts or questions, ask. If you don't, then I will consider the next. Some computer science came to me and asked a question. Can you solve this thing numerically? I said yes. How? I said by using the technique. What is the technique? It is the technique that I mentioned upstairs. By using a system of second order differential equation cannot be directly solved I said directly, it cannot be solved. There is no way to solve second order differential equation. Then how can you handle it? Convert the second order equation to a system of first order. So this is the key. Second order cannot be directly handled, so we should convert the second order differential equation to a system of first order equation. So I showed him how to do it, and then after learning these things, he could solve the problem of solving two second order differential equation in the application problem. So after learning numerical method, you should know this thing. Can you handle third order, second order, fourth order differential equation directly? The answer is no. Then how can you handle it? You make system of first order equation. Because first order equation can be handled by the method that I mentioned, right? RK4. Then how can you convert this question? How can you convert this kind of second order equation into a system of first order equation? So let's do it. So y is y. And then y prime is called z. So this is the key. Y is y. Now y prime is z. Then y prime is y prime. And then y prime is called what? Y prime is called what? Z. And then z prime is y second derivative, right? So this is the definition part. And then after definition part, now application part. Y prime is y prime, and then y prime is called z. Z prime is y prime, and then y second derivative. If you don't like this kind of jump, then I can avoid the jump. You follow me completely? And then after this, we can use the differential equation. What was y second derivative in the differential equation? First column, I don't know to go back to the first column, you read it. Y second derivative is what? Should I really go? Y second derivative equals, y second derivative is what? Minus y plus sin x, right? Minus y plus sin x is y second derivative. Because we use independent variable t, I will use t because I will follow the, of course we can say x and t are the same, but x might have different purpose, so I will use time variable instead of spatial variable x. So this is the conversion. Do you follow me? Then take a look. Is this a first order system or second order system? First order system. Why? Because the derivative is first order. In other words, we are handling the system of first order differential equations. Then once we have it, we can use RK4 or Euler or something to solve this system. So this is the key portion. You need to know how to convert a higher order differential equation into a system. Then what about nth order differential equation? Assume that you have like assume that you have higher order differential equation. What is the idea? How can we make a system of first order equation? So let's call y equals y, and then z equals y primed, and then w equals y second derivative, and then v equals y third derivative, right? So we use a lot of letters. Then what happens? So this is the definition part. And then now real application part will show up. Y primed equals y primed, and y primed is what? Z. And then z primed equals y primed primed, and then y second derivative. Y second derivative is what? W. And then w primed equals y second derivative primed, so y third derivative, then it is v. And then v primed equals y third derivative primed. Then, as you can see, from the differential equation, what can you get? First derivative y equals what? Because of the given differential equation. Minus, this equals, minus what? 2, what? 2v, and then what? And then minus what? And then what? Right? So we use these numbers, and then finally sine t. Done, right? So take a look. We made the system. Is this a first order system? Do you see any second derivative once we erase the intermediate portion? In other words, after this, you hide, and people will not know what you did. So they will think you are handling very sophisticated. Suddenly, we have this system. So take a look. Do you see any second derivative? So you should solve this for y, z, w, v, four functions. Do you see any second derivative here or not? So this is a first order system. So this is the key idea. Once you have a higher order differential equation, you should convert the higher order differential equation into system of first order differential equation. Then if you use RK4, K1 sub, how many are necessary? K1 sub Y, K1 sub y, Z, K1 sub W, K1 sub V. These four things are necessary. And then K2 sub Y, Z, W, V, and K3 sub these things, and so on. After creating these 16 numbers, you sort them, and then sub 1, sub Y are all collected in the next Y height calculation, right? Sub 2 are, sub Z are collected in this Z calculation and so on. Do you follow me or not? If you don't, then I can show you what you need to do if you use RK4 to solve the problem. So essentially done. Then the next thing is the improvement. We learned a very, very powerful method called RK4. In some sense, only for this course, you learn more. But if you need to find the solution of this kind of thing, this RK4 can be applied for ODE problems. But for PDE, you need scientific computation, calculation, requiring, for instance, finite element method, finite difference method, FFT, and so on. But for ODE, RK4 is powerful enough. But for the course, we cannot just stop, because some strange differential equation may require something different than RK4. So we need to learn. So we should consider possible improvements. So how can you improve the method? So we can consider this kind of direction. Implicit method and multi-step method. And I will explain individual things. Multi-step. And uneven nodes and weight. So people develop many things. So weight can be applied, right? So people develop many things, mostly motivated by publication, right? They need to publish. Because nice things are already occupied, they should tweak. So I will explain what kind of thing is possible. When we handle differential equation from x0, y0, especially, we are not caring about, in fact, this kind of base node. It's obvious, right? So base node can be ignored. Then we are caring about this thing. And the next height is the concern. Implicit method is this. Instead of just relying on the known explicit number, an explicit height, we use this height. We use this height in the formula. How? Very strange, right? How? So take a look. Instead of relying on this explicit height that we know, we rely on unknown height. This is called implicit method. So do you clearly see the picture? We want to find some height. So we develop formula. But in the formula, we use unknown height. This is the method called implicit method. Explicit method do not do this kind of thing. To determine this thing, we use this information to determine something, and then use this information to determine something. Eventually, we determine something without using this height. But implicit method development requires this height. Then how can you do it? How? This portion is important. You might hear the word related to this thing. We initially predict the height. We initially predict the height. After predicting the height, at least predicted value is there. Then we can really use the formula requiring this height, and then we correct it. So this method is called predictor-corrector method. We predict and then correct. So it's an implicit method. Do you follow me? So we need to use both heights. One height is explicitly known. The other is the target height we want to determine. Then how do we do it? We predict. Then after predicting it, we go to that place and then correct. Usually it requires a loop. This corrector requires a loop. So we predict and correct. Predict and correct. then why can this have advantage? Why? Because we are handling very delicate values, but if you want to control this value from this position, it is already remote control, right? We are controlling, so take a look, we know this value and we want to determine this height, unknown height. But if we rely on this value too much, from this remote place, we should determine the height. Then there could be error, right? But we go very close to the height, actual height, and then we now control height here. Then it may have better value. That is the philosophy behind this theory. You follow me? So we go close to the point and then correct. So this is called the predictor corrector method, right? Predictor correct method. Now the next possible improvement. We determine, so I will not sketch this X node anymore because it's evenly divided. But using this, we determine this. Using this, we determine this. Using this, we determine this, and so on, right? But instead of using just the previous node, what about using everything that we already accumulate? In other words, instead of just using 1, we can use 1, 2, 3, determine this fourth position. It's called multi-step method. We learned single-step method, but now it's called multi-step method. Using height information 1, 2, 3 that we calculate, we determine the next height information. Do you follow me? So we just do not dump the previous result to calculate fourth position, but we use 1, 2, 3 to calculate fourth position. This is called multi-step method. So we may guess some kind of improvement can be made by this multi-step idea. Then what else is possible? If you use evenly divided space, we may have some kind of problem. So people considered unevenly divided interval. Right? So instead of calculating values at evenly divided interval, people developed the idea of calculating value at unevenly divided interval. Typical example is Chebyshev idea. So I will go to the next page and explain the idea. So if we divide this evenly, then it looks like this, right? Evenly divided subintervals. But when you use Chebyshev idea, then we create the semicircle, and then we divide this arc, right? This arc is divided and then projected, right? Projected. This Chebyshev idea. Then, in some cases, this has advantage. In some cases, this kind of unevenly. So if you look at this x-axis, then it's unevenly divided, right? X-axis is unevenly divided. Sometimes this has advantage over others. So this kind of unevenly divided can be considered to improve the result. And weight can be applied. We already saw the weight, right? In RK4, you saw the weight. Y1 is determined by Y0 plus 1/6, K1, and then weight 2, right? K2. So you saw the weight here, right? And then 2, K3, right? Weight here. And then K4. And then 1 and weight, 1, 1 are hidden. So weight can be used. Not in just this K portion, but in various functions. So people try all possible tweaking to improve the result. Then there are two methods called midpoint method, and some midpoint should not be used. So there are two midpoint methods. So one that should not be used will be explained. This midpoint should not be used. It is using previous step and the next step, skipping the current step. Do you follow me? So as you can see, previous step and next step without current step determines 2h times fn. Right? It's reasonable to consider this kind of direction. But this doesn't work. This completely blows up. So never use this midpoint. So even though it bears name midpoint, when people use midpoint method, it is not this midpoint method. The midpoint method that people use will be explained very soon. But this midpoint should not be used. So never ever use this midpoint rule, skipping the current position. Right? Previous and the next average should not be used because it will blow up very fast. Then what is called midpoint method? That will be explained very soon. So take a look. First, implicit method that you see is trapezoidal method. Trapezoidal method is this one. To determine the next point, we use almost the same idea, but average of current and the next height. But next height is not even known. So do you see the similarity and the difference between this one and Hoynes method? Please check Hoynes method and this method and let me know what is the similarity and what is the difference. Hoynes method and this method look similar. But Hoynes method and this method are completely different, except the pattern looks similar, right? Pattern looks similar, but they are completely different. Take a look at the Hoynes method. Hoynes method is an explicit method. It doesn't rely on the unknown height. This method relies on unknown height. Why? F sub 1 bears what and what? F sub 1 is the, F1 is what? F of x1 and y1. What is the problem term? What is the problem term? y1. We don't know y1. Hoynes method doesn't have y1. This has y1. So this is the similarity and the difference, right? Pattern-wise, they look similar, but in reality, it uses y1 in trapezoidal, while Hoynes do not show y1 at all. So take a look. To determine y1, we need y1, right? This is the problem. So what should we do? To implement this thing, we should predict. We should predict y1. Then y1 is at least predicted. Then we have some value that we can insert. Then we loop the above one many times to get better y1. So do you follow me? y1 is predict or initialized, right? Predict is almost the same as initialization of y1. And then after initializing y1, we have something to improve y1. So this initialized y1, and then corrected y1, have the same letter y1 and y1. But in programming, they are two different things. This is input, and this is output, right? So y1 is input, at the same time y1 is output. So this input gives uy1. This uy1 is used in the loop many times to correct and correct and correct. So this is the first predictor corrector method that you can see. So trapezoidal method is a predictor corrector method. Then how do you predict? How do you predict y1? You may use, so to predict y1, you may use Hoynes or RK4, right? So use Hoynes method or RK4 to determine y1. Predict, you should use, so to predict, you should use explicit method. So to predict, you should know explicit methods such as Hoyne or RK4. So after predicting it, it is nothing but just looping it to better the result, right? To correct the result. Do you follow me? So this is the possible improvement. It's called trapezoidal method. Now, we can consider RK2 instead of RK4. RK4 requires K1, K2, K3, K4. But now, instead of using K1, K2, K3, K4, we use this middle value. So this is RK. So RK2 is this thing. Yn plus 1 is determined by, I will use 1 and 0. Y1 is determined by Y0 plus H times F of X0 plus half, right? And then Y0 plus H F0. So this is the approach RK2. So this is called midpoint method 2. So do you see the point? The previous one can be called the midpoint method, but we should never use the previous midpoint method. But this is reasonable. Midpoint means midpoint, right? Midpoint. So this is called another midpoint method, or we generally categorize this in RK4. It's an explicit method. This is an explicit method. Any questions? Then, instead of really jumping into the next case, I will just overview the next method and then quit. The next method is the method Adam developed. Once we determine series of heights, we have information about these kind of heights, then we can use interpolation theory to somehow connect them. Do you follow me? So the next thing is developed by Adams generally, and Adams used the idea of interpolation. That we can create, right? So using this interpolation, he can predict the solution behavior, right? So Adams developed this kind of idea, and two people were involved. Bashforth was involved, and Moulton was involved. So Bashforth used Adams' idea in explicit calculation. In other words, to determine this thing, Bashforth used previous things. Do you follow me? To determine unknown thing, Bashforth used previous thing, meaning explicit method. After Bashforth took the nice case, the only thing is complicated case, right? The only thing remaining is complicated case. So he took this thing also, and then implicit method was developed. Do you follow me? I'm not jumping into this portion, but I'm just generally explaining the idea. So generally, Adams focused on the points or height that we can find using some method. Once heights are found, then the height passing function might be the solution, right? Height passing function meaning interpolating function might be the solution. That was Adams' idea. After Adams' idea, Bashforth jumped in to use previous heights to determine the next height, meaning exploration method is developed. After Bashforth, Moulton was involved and used the height itself in the development and called completion. So we will learn about this next time, and I will stay here and you can come and ask questions.
How many systems were two-dimensional?
System could be system could have 10 different functions, then it becomes 10-dimensional function. X, Y, Z, all these are variables. So for instance, in the previous example, we used Z, Y, Z, W, V, then already 4-dimensional. In addition to 4-dimensional, independent variable T can be applied, and 5-dimensional function. Yeah. So I only showed you YZ variable, but YZ also bears hidden variable T, already 3-dimensional. But we have 2 unknown functions in 3-dimensional space of T, Y, Z. So we have more variables and more unknown and more dimensions.
We have equations that we have, if we were using f of t, y, 0,
Mm-hmm.
what was f defined as?
Right side of the differential equation. If you have y prime corresponds to x plus y, then x plus is f.
X plus y is f.
Right. If you have y prime equals x minus y, then x minus y is f.
Oh, I understand.
Yeah.
Okay. Okay.
You're right.
Good book.
Very nice book, right? Very nice. But tough to read. Hi.
On the finance,
Mhm.
do we have to come to
No. It is
the
that
definitions?
you just write down those things, description, and then either submit in paper or email me. Yeah, email, you can email. You're welcome. Bye.